close the window.
What's that?
You wanna close the window.
Is the window like open?
Yeah, so.
Oh, maybe that's why it's so loud, huh? I was like, boy, that really is loud. How do you close it? Although it might get stuffy in here. I kind of feel, does the noise bother anybody? I can get used to the noise. I just don't want it to get too warm in here, I guess. And I have no idea how to close it. That's the other reason I'm keeping it open. But if the noise bothers, we can figure it out. Okay. Did I press record? Yes, I did. All right. So we learned about the inside, the glass tube. But we want to now, we're going to learn some other parts of the machine and how it affects X-rays. So I did a little bit more. I wasn't satisfied with my information on Bremsstrahlung and characteristic. And so I just did a little bit. I took a different textbook, one that we don't recommend. I'm not sure how many people have the textbook or if it's online and you guys can share it. But I took a different one and I read their explanation of it. And I just felt like there was a few things that I kind of just bulleted them because I felt there was a few things that people even asked questions and I was like, I just felt like it was fuzzy. So I kind of wanted to just review this. So some bullets that I found that I thought were really helpful. Bremsstrahlung happens the most frequently. So just in general, whatever machine you have, and I think I might have said the opposite on, okay. So I'm glad we're revisiting this. So no matter which machine you have, that happens more often. And it clarifies it more as we go down. So Bremsstrahlung happens the most frequently. Bremsstrahlung produces photons of various wavelengths. You definitely said that, and that's still true. Bremsstrahlung's electrons, they break. So sometimes it's referred to, and this was in the textbook that you guys are recommended, but sometimes it's called breaking radiation because it doesn't come in contact. It gets close, the nucleus draws it in, but then it changes direction. So another way you might hear about it, I don't know if they would say it on the national board, but the breaking radiation because it's kind of putting on the brakes and then it veers off in another. So it breaks before it veers off and it keeps going and it can do the whole thing again until it loses all the power. So I think we said that last time, but I just wanted to reiterate that same photon, X-ray photon that came out of the machine can make Bremsstrahlung radiation multiple times. So it's not just one and done.
It keeps circulating.
Yeah.
Bouncing off.
It just will go in another direction and maybe it goes into a direction and becomes scatter radiation. But it can, oh no, oh my gosh, sorry. Pretend I didn't say that. No, we're still inside of the tungsten target. So yes, in that there are layers because this is where we're making radiation, right? So we're inside the tube head making radiation. And because the tungsten target is not just one layer deep, right? It's not just one layer of atoms, it's like trillions of atoms of tungsten metal. So because it's in that, in this, metal that has just unlimited number of atoms it can interact with, it'll just go off in a different direction. It can make another X-ray photon. So that I already misspoke. I said photon, but it's the electron that's making it. Half of my brain is in the patient's face, and this I know it can get very confusing for you guys because you're like, are we talking about the interaction with a human or are we talking about what's happening inside the machine? And today we're gonna still be talking about what's going on inside the machine, but then we kind of do leave the machine and talk about what happens on the outside. But Bremsstrahlung and characteristic are all in the glass tube. So I have to rewind my mind because I've been thinking past that for the past week. Okay, so yeah, so it can be used over and over again. And then characteristic therefore happens less frequently. So those 2 points I really wanted to clarify because I thought those were definitely murky and I wasn't clear on those. So after reading through it, I was like, oh yeah, that they spelled it out really nicely. So I liked the way that this other textbook talked about this subject. It was an older textbook. Okay, characteristic produces the best photon when it collides with a K-shell electron, but this process can happen with other shells as well. But so it could happen in an M shell, it could happen in an L shell, which I think somebody asked that question last week. But we really focus on the characteristic radiation that happens with the K shell because it's the closest to the nucleus. It has the strongest energy, that binding energy, because it's closest to the nucleus. And so it produces a very high quality X-ray photon. So we kind of, it's like, yes, it can do it with other electrons in different orbits, but that's the one we kind of really focus on. Characteristic radiation involving the K shell can only occur when the machine is set to 70 kVp. So that's kind of what makes it unique, is that it needs, in order to knock out a K shell, I mean, it could knock, theoretically, the electron can knock out, like I just said, other electrons in lower orbits, but to make it this high powered, the best photon, it has to be powerful enough, the electron coming across has to be powerful enough to knock out a K shell electron. And so that's going to be set, the machine's going to be set at kVp in order to do that. If it was set less than that, simply the electron bombarding this target wouldn't have enough power to knock it out.
So theoretically, the machines at the clinic we get a little bit of both, or we just get mostly characteristics, because those are set at.
So if it's set at 70, we know we're getting characteristic, but we're getting both. You can have both happening at the same time. So it's not like this machine, and I think that was also, I feel like it's a question I've had in the past. Someone might have even asked it last Tuesday, and I'm always like, well, I don't know. But yes, that I was very happy to get that answer, because I swear every year someone asks me, and I just, we spend so much time how to acquire a good X-ray that this part comes early, it comes in the beginning, you need it for national boards, but we don't always think about it throughout the rest of the semester. We don't worry about if it's Bremsstrahlung and characteristic, so it kind of goes out of sight, out of mind. But every year someone asks me that, and yet you can get both Bremsstrahlung and characteristic. They can happen at the same time, but you will only get characteristic radiation if the machine is set at a minimum of 70 kVp. So, and you notice on ours that we can change it from 70 to 60. So if we drop down to 60, we'd only get Bremsstrahlung. So I hope that clears it up. I hope I didn't just muddy the waters. Hopefully that clears it up. I'm gonna update my other PowerPoint with this, but I needed to put it on this PowerPoint so that you guys had the best information going forward. And on week 5, is it week 4 or week 5, when we have our first exam, there is a question that asks you the difference between Bremsstrahlung and characteristic, and it's a lengthy answer. So it's like a definition answer. So you know how you try to get all tricky and it's like you mix it up and you'll say, knocks out an outer shell electron instead of an inner shell, so you have to notice those subtle differences and pick the correct definition. So I'll just give you that forewarning that is a question on the exam coming up in a couple weeks. So you really wanted to be able to recite the difference between Bremsstrahlung and characteristic. I'm so dry this morning. I'm sorry, I sound like gravel in my throat. All right, so to review production of X-rays, what are the characteristics of X-rays? Does anybody remember 1 or 2, 3? How do X-rays behave? What kinds of things do they do? How do they travel? How does an X-ray travel? Yes, but after it hits the target and it moves out of the machine, how does it travel? Like a wave or a particle. How else? Does it? When we think of that definition, that's correct. But what did we talk about? Does it have a tendency? An X-ray photon have a tendency to like zigzag? Or does it travel in a straight line? Straight line. And then think about a flashlight. So you can compare a lot of things to a flashlight. We say X-rays, are they visible or invisible? They're invisible. And then like a flashlight where it's strongest at where the light is coming out, but as it gets farther away, it diverges. So it moves in a straight line, but it spreads out. So it travels in a straight line, but it diverges. And does it travel at the speed of light? Yeah, it travels at the speed of light. It's invisible. It has the potential to ionize. Let's see, I have a whole list of them here in the notes. Let's read more. It has no mass, no charge. Particulate radiation has mass and charge, so that's how we kind of just compare those two with just that one piece of information. Travels in waves, short wavelengths with high frequency is the most desirable. Straight line, it can penetrate. So it can penetrate different matter, gas, liquid, solid. But if something is very, very dense, has a high atomic number, instead of penetrating, what does it do? It gets absorbed, yeah, just gets absorbed into it. Okay, so what conditions are necessary for X-ray production? We don't have to recite the whole thing, but what are a few things that we need? If we even want to hope to produce X-rays, what do we need? We need electrons, yeah.
Electrical current.
We need current, we heat up the cathode, yeah. To heat up the filament on the cathode side. To go fast, is that
Focus.
to focus? Yeah, we need a yes, brilliant. We need the focusing of those electrons and then
The stop.
the
The stop. The target is stop. Target.
target. Oh, the stoppage. Yeah, we need a target. So in between the focusing and the target, we just need them to do what? Accelerate. We need them to go really fast from one side to the other. So we need to kind of beef them up with a little bit of energy so that they'll fly over there. What happens? And this is kind of like very practical, and it'll kind of help you think of different parts of it. But if you just go up to the room and on the outside where there's a little container that has all of our supplies, and I flip the switch and it powers on the X-ray machine, what has happened inside the machine? It's getting voltage from the wall, and so the filament's heating up. So it's getting ready. It's like ready to take an X-ray basically. And then when you actually push that button and you hear the beeping sound, what happens at that point?
Explosion.
Yeah, it's exposing we call it's an exposure, right? But like if we think down on a small level and we push the button and have I feel like that sounds weird to have an exposure. But yeah, when we're exposing an X-ray, when we push the button, what happens inside the little glass tube? It actually, do you have
Is that what the electrons start on?
Yeah. Yeah, so we've given it the volt, we've given it the electric, and now they start moving from one side to the other. So that is the exposure time when we push the button on the wall and we hear the beep. What that's doing is it's giving those electrons the boost, the energy, the voltage to fly across and then create. So when we just turn on the machine, it gets it ready. When we push the button, it like actually makes it happen. Good, yeah.
Is that when the thermionic emission happens?
So the thermionic happens when we just turn it on.
Oh.
So when we just turn on the machine and it pulls energy from the circuit, from the wall, wherever it's pulled in, it starts heating up that filament, and then that's the thermionic emission, and then pushing the button gives it that energy or that voltage to fly across. But good question. So yeah, thermionic emission is what happens when we turn the X-ray machine on. It gets those electrons ready to go. So today we're going to ask a few more questions, things that you will want to think about. How are the various electric currents produced? So we know that the machine is plugged into the wall, but we don't need as many volts on the cathode side, and we need way more volts on the anode side. So how does it do that? How does it make not so many volts on one side and like way a lot of volts on the other side? So we're gonna find that out. And then where does the heat go? We kind of know that, remember we talked about it producing like 99% heat, and we already know that there's that copper stem. So we kind of know the answer a little bit, but we'll just talk about that a little bit more. And how do the X-rays interact with human tissue? So we'll talk a little bit more about that. We have already touched on it. I feel like we've said a few things, so you guys might have a little bit of thoughts already on it, and we'll talk a little bit more. And then we have a whole unit after the first exam that's the biology, and that's when we really talk about like more the harmful effects of radiation and what's happening there. So these are the objectives. We're going to talk about direct and alternate current and how it relates to the X-ray machine, how that AC/DC is affecting the flow of X-rays. Identify the internal parts of the X-ray tube head and describe their function. So a few more actual pieces of the machine we have to learn about. Discuss the function of the step up and step down transformers. So we'll learn about the transformers and how they affect voltage. And then list factors influencing the X-ray beam size and intensity. So because an X-ray beam spreads out like a flashlight, we can make it just like a flashlight. You can turn it and it gets more like concentrated and the beam gets smaller, or the beam gets more diffuse. Similar thing with an X-ray machine, it's just fixed. You can't change it. Explain factors affecting X-ray quality and quantity. We'll talk about that. Define types of radiation, describe the process, and identify how each would appear on the film. That objective there, I'm like, I don't know. I'm not so sure I like that second part. Identify factors that influence X-ray absorption. So with the describe the types of radiation and describe the process, that's going to be very similar to how we had to memorize characteristic and Bremsstrahlung. It talks about, although this time it's referring to interaction with matter. So now we're, instead of talking about what's happening at the tungsten target, we're talking about what's happening at a cheek or at a tooth or at a bone or whatever. But it's a very similar, the images are very similar. It's kind of a similar way that you'd memorize those. Okay, so I liked this image because this is the tube head that we were talking all about last week. The focusing cup is here, and inside, nestled inside there is the filament, the tungsten filament. And then this is that copper stem, and you can actually see better, it's copper. And so it's kind of yellow copper colored. And then it's the size of like a pen. So it's really quite small. So we have our cathode side and our anode side, and embedded right in here is a very small tungsten target. And like we learned in the text, it's about only 1 to 3 centimeters from one space to the other. So they're really close. And then you can kind of see this brownish tint to it. So that is the leaded glass. And somewhere on there, it's not leaded. And so it'll let those X-rays come through. So here's a picture of the whole thing. I think we might have seen this last week. I can't remember if this was in the PowerPoint or not. But this is our glass tube with the parts that we learned about in the production of X-rays. But now we have the whole tube head that you actually move around in the room with the PID. And there are parts here that we're going to learn about and how that affects the size and the shape of the X-ray beam. And then also like what's all in the tube head is like usually, like this big. And then we have just the glass. So there's a whole bunch of space. It's like, well, what, this is not a good size representation. This is much smaller. It's just blown up so we can see the detail. But, what else is inside of that casing? Because it's pretty large in comparison to the size, if the tube is like something like that big, it's pretty large tube head that you move around in the room. All right, so the whole thing starts with electricity. The whole thing has to be, if someone asked last week, well, what about the Nomad, which is the wireless one? And had to stop for a second and go, huh? And then I was like, oh, it's a battery because gotta work on something. So, but they all have to have some kind of energy and they have to get their energy from somewhere. And so the ones in our operatories or in the X-ray rooms or however it's set up, they get it from electricity from the wall. So the electric current is a flow of electrons. That's all that is going through from the wall, through the cord, into the machine. It's just a flow of electrons. And they go through the wire or the circuit, and the source is basically like 110 or 220. All of these outlets in here are 110. You can plug in hair dryer or computer or whatever. And then at home, or in buildings, you might have a 210 that you have to plug or 220, sorry, that you have to plug like a washing machine in or something like that. Like you have to plug something bigger in. So most, all these X-rays machines though, I would imagine, I can't say 100%, but I would imagine they all go into a two or 110. Sorry, I'm gonna get my twos and ones mixed up. But a 110, which is just your typical one that you find in a room. So direct current or DC is when the electrons only flow in one direction. So the whole time they're just going, there's never any stopping or slowing down, they're just moving in one direction. That's a DC current. Alternating current, and sometimes you'll hear the phrase AC/DC, meaning it's coming in and out of these two forms, but alternating current means that the electrons flow in one direction and then they stop and they go in the other direction and they go back again. And that is very useful for our understanding of X-rays and the way X-rays work. So electrons travel in one direction, they stop, then they reverse and they go in the opposite direction and then they go back in the direction that they started. And it's just this constant back and forth flow of electrons. Now, what we know about what happens inside of the tube head is that the cathode is what? Is it negative or positive?
Negative.
Negative, and the anode.
Positive.
So if the electrons are flowing from negative to positive, do you think that is going to help or hinder the process? Should help, yeah, because the cathode negative to positive, anode, or negative to the positive anode, and so the electrons when they flow into the machine, they're working along with it, right? They're going when it's AC/DC and they're going from negative to positive. That's the way it all should be working. But when it stops and goes in reverse, what do you think happens to the ability of the machine to make X-rays? It stops it, right? So X-rays are made literally in pulses that are so quick, you just don't even know it's happening. But it's a pulse because those electrons are only flowing the correct way, the right way, half the time. So they're produced in a pulse. Probably was supposed to have advanced my slide and I forgot. Okay, so yeah.
So the X-ray doesn't have an AC?
So all X-ray machines have to run off of an AC current. So it can't be a direct current outlet. It has to be an AC alternating current outlet in order to run an X-ray machine. Because you need, I suppose if it was always going from negative to positive, that would work, but I'm not being an electrician, I think that there would be there might be some heating issues or some stability issues with that. We don't have to know that stuff, although there probably is interesting things to know about it, but not being like engineers or electricians, I hesitate to say too much. Sometimes I theorize and it's wrong, so just so that you know, we use the machines, the tube head, the radiology machines, they use an AC current, a cycle in AC. So the curve above is showing how we have zero energy, as KBP is at zero. And then if it's going from like negative to positive or zero to positive, it goes up. This is the time when we can make our x-rays. And then when it goes from the zero down into the negative, so now it's kind of going from positive to negative, really, even though it's zero, but still it's traveling from positive to negative. No x-rays can be made because it doesn't match up with what's happening inside the cathode anode relationship. So no x-rays are being made. Back up into the positive, x-rays can be made. And so that's why the x-rays are developed in a pulse. So one pulse, you can see like one round of up to the negative, back down to zero, down, up into the positive, back down to zero, down into the negative, back to zero is 1/60th. So it happens 60 times in a second. But for just the time that we make one pulse, is 1/120th. So that can happen 120 times in a second. So very fast, like super fast. So we can do, there can be 120 pulses.
When you hit the button.
Uh-huh.
So from now.
Yeah. And so, and this is more of that information that I don't feel like this information helps you so much practically. It's more like information that they want you to know. But when you push the button and it's like a second and a half or then you should just know that it was not a constant stream of radiation being made. It's a pulse, but it is so fast that it feels like a constant stream of radiation. But in reality, it actually is like stopping and starting, but it's just doing that incredibly fast. And this is what's happening, yeah, like when you push the button. Okay. So maybe just to clarify, because I might have not explained that well, but this right here is not a second. So that's not a second. So a second would be like 120 more drop, you know what I'm saying? So this is just showing, yeah. So this is just showing like one pulse, but it happens many times in a second. So I don't know, I didn't know if I made that clear enough. Okay. So, okay, so more about the power supply. So these two things that are underlined, these two circuits that are underlined are really important. They're questions on tests. You're going to want to, it's going to ask you about the filament circuit and the high voltage circuit and different things about it. So this is all very important information and lots of tests, questions on this information. So for the power supply, so we have inside the machine, there are two circuits and they regulate this flow of electricity in order to help produce that, in order to make the x-rays, to produce x-rays. So the two circuits necessary for production of x-rays in the x-ray tube head are the filament circuit. And what does that sound like? Have we said, yes, exactly. So we've talked about the tungsten filament that's on the cathode side. So the filament circuit, therefore, is going to have a lot to do with what's on the cathode side, having to do with the tungsten filament. It provides a source of electrons by heating the filament. So when we plug it in and that filament starts heating up and the thermionic emission starts happening, that is all due to this filament circuit. But one thing we know is about it is that 110 volts are coming out of the wall, but this filament circuit, in order to heat up and make electrons, does not need 110 volts. That's like way too many. All it needs is 3 to 5 volts. That's all it needs. So in order for it to go from 110 to 3 to 5, which is significantly less, we need something called a step-down transformer. And I should have maybe it comes after this slide. Hold on, I'm going to advance for just a second. I wish that okay, there it is, but I wish I'd put it at the beginning, but I guess I'll just talk through it and then I'll play the video. Maybe after I talk through it and then we listen to the video, it'll all come together, but I probably should have done it the other way around. Okay, so filament circuit, that circuit is responsible for heating the tungsten filament. We know we only need those 3 to 5 volts. We don't need 110 coming out of the wall. So inside the machine, there is something called a step down transformer. And this whole part of the machine and this whole mechanism is controlled solely by the MAs. So on our machine, it says MA7. It's a fixed number. It's milliamperage. And that is the system that controls this whole side is MA. So back in the day, if you could have lowered your MA or raised up your MA, you would have been probably controlling a little bit of the voltage, and therefore you would have been controlling how hot the filament got, and you would produce either more or less electrons. But nowadays it's just fixed. Almost all machines, the MA setting is fixed. But that's what controls this side. And we're going to talk a lot more about what the step up and step down transformers. Just kind of getting this out here on this slide. So the other half that we have to think about is what's going on the anode side. So that the filament circuit is happening on the cathode side. So now we have to think what's happening on the anode side. So now we have a high voltage circuit. The high voltage circuit is going to be responsible for amping up electricity, amping up the volts so that we can get those electrons to fly over at high speed. So again, out of the wall comes 110 volts, but we need way more than that, like way more. So we need 65 to 100,000 volts in a very short amount of time, like not just running crazy, but in a very short amount of time, we need a lot more voltage. And this side is going to be controlled by the kilovolt kVp. I think it's technically, I just say kVp. I think it's technically like kVe or something, but for our purposes, we say kVp. And that you can control a little bit on our machines, but not very much. Older machines, you could control it quite a bit. You could dial it up, dial it down, but our machines, we just leave it at 70. But to get the voltage from 110 to like 100,000, now we need a different kind of transformer, similar concept, but it's gonna be made differently, so that now it's called a step up transformer. And obviously you can see down is downgrading the voltage, up is upgrading the voltage. So that's the whole point of these transformers, is down regulate the voltage, lower the voltage, or increase the voltage. That's what the transformers do. And then an auto transformer basically just keeps everything sort of stable and steady. If we didn't have transformers, the lights in our room would surge, we'd get flickers, the computer monitor would maybe surge, or, power would like come in and then kind of die down and then come in again, because it just can happen that way. Not an electrician, but it just can. And so they need this moderating system that just gives a nice, steady, even flow so that we don't get these power surges and it doesn't blow out our computers or pop a light bulb or whatever. And so the same thing is there are auto transformers in the radiology machine as well, but we have these specific transformers that are purposefully trying to way scale back the voltage or way increase for these specific times that we need that extra voltage or decreased voltage. Okay, so the transformer coils. So on the step up and the step down, oh yes, question. Say it again, the first part.
The preliminary circuit, does that happen on the anode side or the
The high voltage circuit, that happens on the anode side. Sort of, for the most part, that's what you need to think about. And the filament circuit happens on the cathode side. Sorry if I took longer to answer. But I think Max was going by right as you were asking that question. So I was like, I can't hear you. Okay, so the transformers has two sets of coils, and we're gonna have some diagrams to look at and watch a video, and so this will all kind of come together. So there's two sets of coils on a transformer. There is the primary coil. Yeah,
Question. Is the filament circuit a step down transformer?
it is. The filament circuit is step down. Yeah. So there's the primary coil, that's the input. So that's the first coil that the electrons will reach when it comes out of the wall and it's going down the cord. The first thing it'll come to is the primary coil. And then a really cool thing happens inside this transformer, which we don't really have to understand very much, but the video kind of highlights it a little bit. But then the secondary coil is gonna start to activate. And so that is the output. So the secondary coil is the one that's responsible for whether or not the voltage goes up or down. Because the primary one is always gonna get 110 volts from the wall. It's the first one, it's the primary, it's always gonna get the 110 volts. It comes first. But the secondary coil is gonna either push them up or push them down. And then it's gonna go on from there. So when there are more turns in the primary coil, and this is just not gonna make sense until we have diagrams. Okay. Let's do that. No, I don't wanna do this yet. I don't. Okay, so basically, I'll just draw it so that these words make a little bit more sense. So the transformer is just like a kind of like a box, maybe thicker sides, and then we have the primary coil. So we have, if there are more turns, and this is just metal coil around it, and it's an iron core. So if there are more turns in the primary coil than the secondary coil, the voltage is going to be reduced. So fewer turns.
What does it determine which one has more coils? Like which one has more turns, more turns.
Yeah, so secondary, so this is called your secondary coil. This is your primary coil. So we just know that for the electricity, the secondary coil is going to be our output, right? So if you have a transformer where the primary coil just has more turns in it, like there's 100 versus 50, then we know that the whole are you mad at us? I don't know. So we just know that the whole voltage is going to be reduced because this is our input and this is our output. And there's less coils, so it's reducing the voltage. So we would call this, what would you call this? Step up or step down? Yeah. So this is our step down, and it's controlled by MA or KVP? MA. And is it on the cathode side or the anode side? Cathode side. So you almost basically know everything you need to know. Now you memorize that and you'll get an A. Okay, but we're gonna keep moving. So then we have, for those of you who couldn't see that one very well, I'll do this one over here. So then we have on this side, we have another transformer. It's an iron core. We have lots of pictures of it coming up. But on this one, when there are fewer turns, this is our primary coil. So when there are fewer, I know. This is loud. When there are fewer turns in the primary coil than the secondary. So here's our secondary down here. And this is just metal wrapped around the iron core. So that's what it's diagramming. So when there are when the 110 volts come to here, and then they have their cool interaction, and then the secondary coil starts activating, it's gonna increase voltage because there are more turns in the secondary coil. So this is output, and it's gonna increase. I have to put my arrow going the other way. So this is output after it reaches the second coil, and it increases voltage. So the secondary coil is responsible for either increasing or decreasing, and on this one, so then what would we call this one? Step up or
Still step.
step up. And which circuit, which side is this on?
I know.
The anode, and it's controlled by, and it's controlled by kVp. And this one is a little tricky because you'll see in a diagram, it kind of is connected to both sides. But for your knowledge of what I want you to know for tests, just think step up, kVp anode side, step down, MA cathode side. And there's a reason why it has to be connected to two and both sides, and it makes sense, but I still want you to kind of predominantly think about those in the two different ways. Okay, so just the next couple slides literally just keep repeating this concept so that you're get really comfortable with it. Okay, so here this is just focused all on the step down transformer. So now we're just putting in some visuals for you to look at, and then these are all the important points that you want to memorize. So the step down transformer, it heats the filament circuit. So that's one, that could be a test question. It heats the filament circuit. It is controlled by MA, milliamperage. There are fewer turns in the secondary coil than the primary. That is why it is a step down. So it's this one over here. And that in all functionality, it's reducing the voltage from 110 to 3 to 5 volts. So that's what it's doing. And then this is just showing, just like what I was drawing on the board. So here's the iron core of the transformer, and then the filaments wrapped around, or the coils wrapped around it. Primary, there's fewer turns. There's more turns in the secondary. So this is a step up. And then the red arrow is pointing to this one, which is the step down, because there are fewer turns in the secondary than the primary. So this is showing a step up, and that's showing it, and they're labeled there, but just so you know, the red arrow is pointing to the one that all of this information is about. It's about this one. And this is, don't worry so much about this picture. This shows auto transformer, and it has some info. Don't worry, you can kind of cross that out on your notes if you want to. Okay, so that's step down. So step up, same picture, different information. The step up transformer inside of the machine, it controls the high voltage circuit. It is controlled by kilovoltage. There are more turns now in the secondary than the primary, and it changes the voltage from 110 to 65. You could probably say 60 to 100,000, because when it says 60 kVp, that's correlates with 60,000 volts. I'm almost positive. So 60 to 100,000, but 65 to however. That I don't know that that's, if you see a very, very large number, you know that we're talking about the step up and the kilovolt side, the kVp side. And so then the red arrow is pointing to the step up transformer of those two. So this slide and the one previously has nutshelled everything you want to memorize about this process. I could have a question asking about which circuit does what, which is controlled by what, the voltage is going from what to what, it's controlled by, MA or kVp, what side is it on, cathode, anode. Those are the types of questions you're going to be asked, and they're usually just very short questions. But usually what trips people up is they read questions too fast, or there's options that are sort of similar and they just didn't learn it well enough to be able to differentiate. You know, when you take a multiple choice test, there's always two usually that you can throw out almost immediately. Like people are usually like, yeah, not that, not that. And then they're like, oh gosh, between two. And that's just like a very classic way to take a multiple choice is like throw out the two and then the one that's like your gut instinct, go with that one unless everything is screaming at you that no, I'm thinking about this wrong, you know. But usually your first choice, your gut instinct is usually right. But usually people have to toggle between two. I just found money in my pocket. It's only $1. It's like that. It's like I know it's fun when you find money after like a really long time.
Yeah, it's like
$20 in a coat or something. Yeah. I'm not getting supply now. It's nice. Okay, so auto transformers, this is pretty much all you really need to know about the auto transformer. Gives the ability to alter kilovolt of the X-ray machine. A single coil around an iron core serves as primary and secondary. That's kind of summarizing what we said, and so all you really need to know about auto transformers is that they sort of just regulate. They make it so the machine doesn't surge and like pop a breaker or something like that. Everything, you know, because there is this increase and decrease of voltage, it basically is there to, I think, in general, keep everything flowing well and to recover from maybe these surges. I don't ask you a lot. I don't even know if I ask you questions on the auto transformer, honestly. I think it's nice to know that that's the purpose of an auto transformer, but we don't really go in depth, so.
All the machines have those stuff, like the auto ones.
That's, you know, I don't really know if all of them, I would very much assume that they do, but if they are engineered in a different way, you know, that kind of goes a little. Because there are so many different machines. I would assume they do. If electricity is a part of it, I would assume, but like I said, I'm not going to test you on it, so don't worry about it. But you're certainly welcome to find out and tell me. Okay, so let's watch this little video. This one, I think some of it goes a little more than what we need to know, but I really liked some of the visuals. So let's watch this here.
Performance, ability, affordability.
Oh, it's a commercial. Like what? Oh, okay, another commercial.
Under our roof, American Family Insurance.
Hello everyone, and welcome back to Electrology. Today, we have an electrifying topic to dive into: electrical transformers. Transformers are fascinating devices that play a crucial role in our everyday lives. In this video, we'll demystify how electrical transformers work and explore their various applications. So, let's jump right into it. First, let's lay the foundation by understanding what a transformer is. At its core, a transformer is an electrical device that transfers energy from one circuit to another through electromagnetic induction. It's like magic. Check out this simplified diagram. When alternating current, AC, flows through the primary coil, it creates a magnetic field. This magnetic field then induces a voltage in the secondary coil, thanks to electromagnetic induction. Now, let's differentiate between step-up and step-down transformers. Step-up transformers. In a step-up transformer, the secondary coil has more turns than the primary coil. This results in an increased output voltage compared to the input voltage. As the primary coil's AC generates a magnetic field, the secondary coil's extra turns lead to a higher induced voltage, causing a step-up in voltage. The mathematical relationship is expressed as V1 by V2.
You do not need to know that.
Thank you.
N1 and V2 of the primary and secondary voltages, N1 and N2 of the corresponding turns. Step-down transformers. Conversely, in a step-down transformer, the secondary coil has fewer turns than the primary coil, resulting in a reduced output voltage compared to the input voltage. The fewer turns in the secondary coil cause a lower induced voltage, leading to a step down in voltage. Transformers come in various configurations, including single-phase and three-phase. Single-phase transformers. These transformers are designed for single-phase AC power.
I think
They
that,
have two coils,
I think the rest of it
one
is
with
stuff that
second
doesn't really apply.
transferring energy. They're commonly used in residential applications. Three-phase transformers. Three-phase transformers have three primary.
Yeah,
and
I
three
think that's the most helpful. Feel free to watch the rest of it, but some of it is not pertinent. It goes back toward the end of the video and just sort of talks again about the coils. So I like this one because of the emphasis on the primary, secondary, and it was a visual. But there is stuff that doesn't really apply to us very much, so.
coils. Field group.
Okay, just again, another, so this one is another visual, but what it does that I hesitate to make too much of it because I don't want to confuse anybody, but at the same time, it is what it is. So if you notice the step down, we say the step down is controlled by MA. And it's on the cathode side. So we have the tungsten filament, we have the focusing cup. This is the cathode side. And so this is negative over here. So the step down transformer is only over here. But if you look at the step up transformer, there's a line that comes over here to the anode, but then there's also a line that comes down here to the cathode side. And it makes sense because we need the electrons that are on this side in the thermionic emission cloud, the electron cloud, that are being produced by thermionic emission, we need those to get get a high voltage, right? We need them to have power to fly over here. So the step up sort of like works on both sides of it to like zap it and get them to move fast. But I still want your main understanding of it to be like it has to do with the anode side because we're trying to get them to fly over to the anode side. It's controlled by kVp. It increases voltage, and that the step down is just on the is just controlled by NA and it's just on the cathode side. So that can be a little bit like confusing because this technically kind of does reach both sides, but when you know why it reaches both sides, it's doing that just to help get those electrons to be fast moving electrons, so you get a high voltage. Is that clear as mud, or does that make sense? But this diagram draws it out nicely, I feel like, so you can see. Okay, again, it's just another picture. It shows our little glass tube head. It's making the step up and the step down very big. And again, it's showing this one just over here on the cathode side, but this one technically on both, but we still know that we're gonna focus it over here. And then over here it shows, I like it, it's kind of old fashioned, but it shows, like it's plugged into the wall. So we got 110 volts. But those 110 volts are gonna make their way through the machine, and the step down transformer is gonna make them 3 to 5, and the step up is gonna turn that 110 to 60 to 100,000. This machine is showing how MA can be different, and the kVp can be set at different, and you can also adjust the timer, the impulses, but that's all things that, for the most part, are preset for us. Little bit of kVpe we can change from 60 to 70, and then we can change our exposure time. But this is showing like a machine that would have a lot more ability to adjust numbers. But it kind of puts it all together. So I like that picture, even though it's a little bit dated. Okay, so that kind of that's that topic. We're gonna move on from there. Maybe 5 minutes. Let's take a 5-minute stretch break. Get some bathroom break, get some water, stretch, let our brains kind of, yeah.
It's very successful. And the example that it's asked about the same
A lot of times it's only asking about one or the other. So if it'll say, it might say something like, the negative side of the tube head is which one, and then you would just say, But usually you don't say cathode and anode, and when did you ask about high school? Yeah, sorry. You just say, yeah. Oh, sorry. I was like, as I was saying it, like, I was asking about something. So yeah, you would just say anode, you don't, even though technically it's kind of attached on there, you don't have to. Good question. I like the clarifying questions.
Really? Yeah, me too. No, I get her like studying like. Oh, yeah, there's a cover behind the show. Yeah, but I'm trying to like hold this, yeah, and no, so like.
Sorry, very distracted. I heard what you said. It doesn't matter on the size of the person, but do I want you to have a longer exposure time?
Everybody.
No, but that's why we use that, that's why we use the control panel and it has like the teeth. Oh my gosh, that doesn't look like a tooth. That's why it has like the teeth that, so this is gonna be your default. You know, like pick, oh my gosh, pick a tooth, pick the tooth that matches where you are. But then the more comfortable that you get with taking x-rays and the more sort of intuitive, all of this stuff is just going to feel like, you know, you're a fish out of water and everything is so new. But in a very short amount of time, all these pieces come together and you feel more confident and comfortable. And so you'll be able to say to yourself, I took this x-ray and it came out kind of light. I think I'm going to raise the exposure time a little bit. But in the beginning, just follow the yellow brick road, follow the buttons that you're supposed to. And then and then when you go out and work in an office, they might have a different machine and they might have to tell you the tricks of that machine, you know, or something. And so, but yeah, basically it's not so much about always having more exposure time. It's just doing the exposure time that's necessary. And this is a good default system when you pick the button that matches the area. That's a good place to start. Okay. You guys are gonna like hate me a little because I just resumed recording and we talked a lot just now. Somebody needs to be my reminder. I always have a reminder in every class and nobody has stepped up. So someone has to help me remember to do this recording. So because that is the case, if anybody feels very confused on that slide, please come to me. We'll talk about it some more. I'll for next week, I'll try and have like a worksheet where we'll just review some of those points. This does give a little bit more of a clarity on the distance piece. When we talk about distance and we talk about it more in the units that are to come, we focus on three things. We focus on what's happening at the target. So what's happening at the tungsten target, where the x-rays are actually produced. Then we talk about that in comparison to like the first thing that gets hit, which is obviously the cheek, right? Those are the first cells, the first atoms that the x-ray photon is going to interact with. But then we have our object. Our object is always our tube. That's the whole point. We want to get a good picture of the tube. So then we have the distance between the target and our object. And then we have the distance between the target and the receptor, which is our sensor. So some older textbooks will say film, like the distance between the target and the film, but we know it's a sensor. So we have these different distances. And if you move things around, if there's a lot of play here, if you move the film, the sensor, and the tooth or the object, if you move it from farther away to closer, you're gonna affect the image a lot. If you move your target ultimately from these things, you get some distortion or some clarity. So there is things that happen with distance, and we'll talk about that more later. Okay, so the relationship between exposure and this, basically, we might have already said this, but both have a direct effect on the number of X-ray photons being produced in an X-ray beam, the exposure time, and MA. And that's just because as we are pushing the button, we're taking those available electrons, and I said this before, but the thing wasn't recording, so this is good. But as we're pushing the button, we are taking those available electrons that are determined by the milliamperage or MA, and we're giving them that high voltage so that they fly across. So that's why both of those are going to affect our quantity, because whether or not we have a lot of electrons or fewer electrons is ultimately going to determine how many X-ray photons, and then how long we're letting that process happen is also ultimately going to control how many X-ray photons. So milliamperage required for a given exposure time is inversely proportional to the exposure time. So what that means is, and we're gonna talk about the inverse square law here in just a second, which again, that's like my nemesis. So I get very simple. It's a very simple concept because I don't like it. Mathematically, it's hard to explain for me. But so the higher the milliamperage, it's going to require less exposure time. Ultimately, that is completely out of our hands. We've said it a million times. MA is fixed. All we can control is exposure time. But back in the day, if you raised up the milliamperage, if you increased the amount of electrons, you could decrease the amount of exposure time. They're inversely proportional. As one goes up, you don't need as much of the other. As the other one goes down, you need more of the other.
That's the inverse square law.
It does affect the word inversely proportional, it's the same as the inverse square law, and it has more to do with distance, and we'll get to it in, I think, just a second. I think the next slide. Yeah.
So if more exposure time is gonna be less in milliamperage?
In theory, again, it's nothing that we control, but if you're gonna have a larger exposure time, if you were able to dial all these things in, how you would do it is you would raise MA, and then you wouldn't need as much exposure time. But so they're inversely proportional. We can't change MA. So this is one of those facts that they could be tested on the national board. They want you to realize that if this was like those days when all the machines needed to be adjusted by hand, they're trying to let you know that if you're going to have one higher, the other one can be dialed back because they're inversely proportional. If one is up, the other can go down, and vice versa. So that's the concept that they're trying to teach. It's not very applicable though to us because we can't change MA. But we can change a little bit exposure time. We can change that.
So you're saying the larger exposure time, less MA,
Yeah.
the greater MA, less exposure.
Bingo. Yes, that's exactly it. Okay. There is a concept called the inverse square law, and there is a mathematical equation. Now, I loved science, but I hate math. And no matter how much I try, there's a very simple equation. Honestly, it's not hard math, but I think the pressure on me is just too great. And every time I think I'm going to do the equation, I'm like, I just can't do it. Because I'm afraid I'll just confuse everyone. I do not test you on the mathematical equation. I doubt the national board. I highly, highly doubt the national board will test you. They're multiple choice, so they don't really have a system where you could work out long math. But I can tell you what it ultimately means, and you can almost do like a problem in your head, really. And so there is a fractional, form, but I just skip that. And I just don't talk about it. So this is the concept. The intensity of radiation is, again, that word inversely proportional to the square, and that's where it gets confusing. It's fractions. The square of the distance from the source of radiation. So inversely proportional means that as one variable increases, like as the distance increases, the other will decrease. So we're going to have this inverse relationship as these numbers change. When the source is going to be at our tungsten target. So the source is where the X-rays are developed. when the source to receptor distance, the receptor is our sensor, is increased, the intensity of the beam decreases. Can anyone think of a visual that helps explain this? What does this look like? A flashlight. That's literally what it's talking about, but it has it in a mathematical equation. So in my side notes here, if the distance is doubled, so if the distance between the tungsten target and the receptor is doubled, and what that means in practical terms is the PID that sticks out, the cone that comes up to the patient's cheek. Sometimes those are really short, like maybe 8 inches. It's really short. Other times it's like 16 inches. It's twice as long. It's like a long PID. So if the distance is doubled, let's say from like 8 to 16, the beam will become 1/4 as intense if the distance is cut in half. So if the distance is shorter, it's gonna be more intense. And if the distance is longer, then it's gonna be more diluted or more diffuse. And if the distance goes from an 8-inch to a 16 and everything else stays the same, MA, KBP stays the same, then the beam intensity will decrease because it's traveling longer, it's spreading out. You have this same, let's just give it a number, let's say 100 X-ray photons come out of the machine. You're gonna spread 100 over a greater area than if this distance is shorter. Those 100 are now going to be all packed into this area instead of this area. You still have 100. They're just, it's either putting all of you guys in a smaller room or all of you guys in a bigger room. That's essential, and it depends on the distance. So visually, conceptually, I totally get it. That's where I want you to be. There is a mathematical equation. I might even have the formula written up. Oh no, I think I even took it down because I don't even want to have to try and have you guys follow along with it because I feel like I'll just mess up. But here's another way. I feel like this is something you can kind of do in your head though, because we know if we go back to this slide here and you look at this, so here's doubled. So we could say an 8-inch PID, and we could say the times 2, we could say a 16-inch. So if it goes from an 8-inch PID to a 16-inch, then we know we need to increase the exposure times 4 because it's going to be that much weaker, that much more spread out. So we need more exposure time so that we have more X-rays, and so we don't lose the quality. We don't get like a whiter washed out X-ray. But if we go from a 16-inch PID to an 8-inch PID, we can dial down the MA, we can dial down the exposure time, whatever we can have control over, because we're going to have more intense, more kind of all in one smaller area. Those photons are all going to be in a smaller area.
So in theory, it's better for the patient to have the shorter PID on a machine. Not gonna get X-rays taken, like ones with the long, or is it like?
It actually really, in theory, it depends on, as long as collimation plays a role, and we'll get to that. But also the exposure time and the power. So this kind of makes you think like shorter would always be better, but because we have different things inside the machine that kind of help to control the spread, you can have a long PID and it's fine. So this is like, you kind of have to isolate some of these concepts. Like you have to be like, okay, this is the concept of the inverse square law. This is what's technically happening. But then they put all these, they engineer all these things that kind of affect. So it's not always just that black and white,
Okay.
but it's a very good thought. It makes sense what you're saying. But yeah, there are other things that affect the display of the beam. But so this next one is just basically, here is a video that I don't feel like I have time to play it, but please do watch it because this shows it visually. This is a good visual. Maybe I do have time. I don't know. Let me see. Do I have time?
Pretty fine.
The inverse square law. To understand the inverse square law, we have to understand the nature of the X-ray beam. When the X-ray beam is created at the anode target, it's created in an isotropic fashion. That means it's created equally in all directions. The X-ray beam is also described as divergent. This means it's spreading apart and becoming less intense as it travels through space. So here's an analogy. A flashlight has a divergent beam, just like the X-ray beam. In other words, the brightness of the flashlight depends on how close you are to the lights. When the distance from the lights increases, the light spreads out and becomes less bright. This is described as a decrease in intensity. When the distance from the light decreases, the light becomes more concentrated and appears more bright. This is described as an increase in intensity. The change in intensity due to a change in distance is called the inverse square law. So here's what that relationship looks like. When the distance increases between the X-ray tube and the point of measurements, this results in a decrease in the X-ray beam intensity. The opposite is also true. If the distance decreases between the X-ray tube and the point of interest, then the X-ray beam intensity or quantity will increase. The inverse square law affects several aspects of a radiological procedure. Notice that when the X-ray tube position changes, there's several other variables that change. The X-ray beam intensity at the patient is also changing. When the tube position changes, the patient dose changes. And last of all, when the tube position changes, the receptor exposure is also changing. That's the number of photons striking the end receptor. You should know that all of this is assuming we're using a fixed technique, not automatic exposure control. So all of these relationships follow the inverse square law.
Does anybody have a charger?
The beam intensity at the patient decreases.
I am so
The
sorry.
patient dose decreases.
My computer battery did not
decreases.
say.
Here's the opposite is also true. If we decrease the distance.
My battery did not used to go this fast.
Closer to the patient, the intensity of the patient increases.
I don't think that's
The
the.
patient dose increases and the receptor exposure increases. I'm sure you'll be excited to know that there is
Is
a
that-
formula for the inverse square law that looks just like this. So how do you use that formula? That's the topic of our next lesson on inverse square math. If you enjoyed this video, I encourage you to visit cloverlearning.com and explore our robust.
Thank you.
collection of
Okay.
video-based courses serving.
Okay, so I'm gonna move because we only have about 10 minutes. I'm gonna move fast. I'm gonna move fast. Okay. We have talked about the importance of the actual X-ray, quality of the X-ray photon. And what we talked about a little bit before was the wavelength and frequency. So when we have KVP set at a lower level, the energy, overall energy is going to be lower. And so that's why we got to find that ideal KVP, which it's already done for you. But knowing that that is going to affect the energy of the X-ray photon is really important. So in general, what we're looking for are short wavelengths because they penetrate better, they have higher energy and a higher frequency, and they go through things. And this is a little bit of review. I think we sort of talked about this a little bit with the last unit, although it might be fuzzy because we've learned a lot of things. But that's going to look like this down here. So this short wavelength, high frequency, that's ideal. And this is going to be the ones that we want to try to weed out, longer wavelengths and a lower frequency. So the red circle is saying this is what you want. This is ideal. And then this image down here, it's all of this together. So it's showing this here is a lower KVP, lower frequency, longer wavelengths, lower energy, and see how this is an atom of matter. See how it gets stopped easily? When we start raising the KVP, that gives the X-ray photon the ability to penetrate a little bit deeper. And then when we have our ideal KVP, it penetrates really well and it probably is going to get over to the sensor and strike the sensor. Now, not all photons have to strike the sensor. That's why we have that variability. But this is just showing you how KVP is going to affect the ability of the X-ray photon to penetrate deeper. There are some things though that we're going to do to weed out those kind of weak, useless X-ray photons. And what we're using are a couple things, a filtration system and a collimator or a collimation system. So the first thing is a filter. So this is our metal tube head that we move around the room. This is what we actually grab onto and move around, put up onto our patient's face. This is the PID. This is our X-ray beam coming from the target, coming out and traveling down the PID. They stick a filter in there, and it's important for you to remember that that filter is made of aluminum. So that is an important, that can be a test question. What's the filter made of? Now the filter is made of aluminum, and it's usually made from in different thicknesses. So if we have a machine that is set below 70 kVp, it's going to be 1.5 millimeters. If it's set above 70 or higher, it's going to be 2.5 millimeters. So those two bullets are questions, have been questions on tests in the past. So the location of this, just to clarify, is not part of that little glass tube that actually generates the X-ray photons. It is basically at the base of the PID. You can go into the X-ray room and you can look straight down the PID and you can see metal, and that's what you're looking at basically is that filter. There could be like a plastic covering or something, I suppose, but that's basically where this filter is. It's right at the back end of the PID. So this is called half value layer. It's the thickness of absorbing material, aluminum. It's made of aluminum, necessary to reduce the intensity by half. And you might be like, why are we making this beam less intense? I thought we were supposed to make the beam more intense. But really all it's doing is it's reducing the useless photons. So it's just reducing the photons that aren't very useful to give us a very good picture. Yes.
Did you say on the last slide that the aluminum filter, its purpose is to absorb useless low energy photons?
Yes. Yeah, exactly. Collimation is the next piece. And the collimator is essentially, sometimes people think of it as the whole PID, but really it's usually just like a diaphragm. The PID can control the size and the shape, but really it's the diaphragm at the end. So we have the aluminum filter, and then we have this diaphragm that's like shaped like a donut, but this is made from lead. So don't get these two things confused. We have the aluminum filter, which covers it completely. All the X-ray photons have to go through the aluminum filter, and it filters out the weak ones. But now we have this lead collimator, and that's it's like at the same end as the aluminum filter. And this is just going to totally absorb a certain amount of X-ray photons. High ones, low one, high power, low power. This is going to totally absorb them. And it's going to restrict the size and the shape of the X-ray beam. So notice how this one here is rectangular. And you might not have seen yet, but in our rooms, and this is going to make the dental assistants who've taken X-rays for a long time, if you've never taken an X-ray with a rectangular PID, it's considerably easier to cone cut or have a beam centering error. So this is going to be a little bit of an adjustment, even if you've taken X-rays for a long time. But the collimator can be rectangular or it can be circular. But it is going to restrict the size of the primary beam that comes out of the end of the the machine. And this is just a diagram that kind of shows, we use a rectangular one, so if you have a circular one, there's gonna be a little bit, there's a little bit more of a splay of those photons, and so it's less likely that you're going to cone cut, because you have a wider field of view, right? But if you use a rectangular one like we do, it restricts it, and it's much easier to have a beam centering error.
How do we avoid that? Like when we're positioned?
We're gonna,
The XCPs are rounded. which is
yes,
like
and so
tiny.
it's a bit, you have to be, that's very good, you're thinking like from
I'm like-
experience, you're like, what am I gonna do? And so we'll show you in lab, it's actually I was surprised how it did not increase the amount. Our old ones had rectangular inset, and the students put the rectangular PID in the inset of the target. It had this little rectangle inset. We still got cone cuts. And then when we tried these out, I actually almost thought it was easier to avoid a cone cut, but I know it doesn't seem that way because it's all just one big
With the new
circle.
XCPs, you mean?
Yeah, with the new XCPs, I think it's not gonna be a problem. I think it might even be better, but we'll get to that in lab. Okay. Back to fly. So this is an image of, this is highlighting our round collimator versus our rectangular collimator. The key point that I want you to take home from this is that we are reducing the amount of X-ray exposure for the patients when we use our rectangular collimator. And that is why we do it, because you can take twice as many X-rays and on somebody and have the same amount of exposure that you would with a standard round collimator. But you are gonna probably take more X-rays because you're learning. So when you have your patients next semester and you have an FMX or a bite wing, you'll probably end up taking more films than you would normally take if you've been practicing for 2, 3, 5 years, because you're learning how to do it. So we have a lot more leeway. So it reduces the radiation by 50 to 60%. And that is oftentimes a question that I'll ask you guys on a test. Rectangular collimators reduce the radiation by 50 to 60%. That is why we use them in our clinic. Probably you're not going to use them in the real world. The real world. Out there in the real, but they really do reduce the amount of exposure. So this is a diagram that I really want you to highlight two things. So here we have our primary beam coming off of the target here, and it has to go through the aluminum filter, which is highlighted here, and then it has to go through the collimator, which is here, and this is just, it's hitting the inside of the machine here and here, which is also made of metal, or I think it's lead lined. So it's hitting that. So you see how the beam went from this all the way down to this. And then notice it still splays, so there's still this divergence, but notice the beam is much narrower than it would have been otherwise. See there, it reduces that beam dramatically as it's coming out. I cannot talk on this because it's too complicated and I need more time. So this is what I'm gonna do. I am gonna pass this out to you guys.
You have to tell me this or this for us.
No, that's for you guys. Okay. I'm gonna pass, so take one and pass the take home quiz. I'm thinking out loud how I'm gonna do this last bit. I think what I'm gonna do is I'm gonna go to my office and I'm gonna record the rest of this lecture, and then I'm gonna post it. It'll probably only be another maybe 10-20 minutes at the most, because it's like 12 more slides, and some of them go very quickly. But these primary radiation, secondary radiation, and scatter, I'm gonna go and I will record it and I'll post it. And then next Tuesday we're basically going over things that we have talked about to some degree. We talked about different x-rays, PAs versus bite wings and anterior, posterior. So that might go a little bit faster. It's not such heavy material. And so I might be able to like start out the class by reviewing this, but listen to the recording through this week. And so you'll come into next Tuesday's class, at least having heard me say it, and then we can kind of talk about any clarifying questions that anybody might have. Because this content is on the exam, and I want you to have gotten it and had it delivered to you guys in a way that you have an opportunity to fully feel comfortable with. So I'll go through it I'll record it'll be a separate short video. The recording from this class will be posted, and then I'll post a second short one. And so listen to both of them, and then we'll review it. That quiz is going to be